The universal method. Collect a set of phenomena. Observe the phenomena for patterns. Use the patterns as principles for a theory. It was through this universal method that Darwin developed the theory of natural selection. By observing various species, from tortoises to the finches of the Galapagos, Darwin identified regularities of variation, heritability, differential survival, and reproductive success, forming the foundation of his theory. Similarly, Alfred Russel Wallace independently reached the same conclusion after years in the Amazon rainforest and the jungles of the Malay archipelago, observing and collecting beetles, butterflies, and other organisms to sell to private collectors and museums. Assume universality. Aim for universality. The goal is universality. All great scientific theories were developed using the universal method, whether the founders were consciously aware of it or not. It is how Kepler and Newton discovered their laws of motion. It is how supervised learning in artificial intelligence operates. In genetics, regularities in genetic material are used to determine a theory of ancestry, showing how organisms are related. Even the act of finding a fitting function for a set of data points is an application of this approach. When scientists perform experiments, make observations, and plot and fit resulting data, they are applying this method. There are no limitations. This method of pattern recognition extends beyond science. It is how Joseph Campbell identified the monomyth, gathering myths from different cultures and times, revealing the pattern of the hero's journey. It is how Aristotle wrote politics, establishing his principles of rule by one, rule by the few, and rule by the many, by observing the different forms of government across the city-states of ancient Greece. It is how Robert Michels discovered the iron law of oligarchy by studying the evolution of democratic organizations. It is how the Buddha developed his theory of human suffering from his observations of ordinary life outside the walled garden of his palace home. And it is how the Buddha arrived at a method to end individual suffering, by venturing into the world, to see, learn, and experience. And it will be through this method that we will find and describe a complete theory of intelligence. The steps of the universal method consist of 1. Collect a set of phenomena by exploring, experimenting, or observing the environment. A display case of beetles is a collection of phenomena. Butterflies in an observatory are a collection of phenomena. A stack of object-labeled photos. Grandmaster chess games with recorded move sequences. Recordings of a spoken foreign language with their translated subtitles. The set of all biological organisms, observations of celestial objects in the night sky, or studies of physical motion, all are collections of phenomena. To produce an effective theory, our collection must be high in both quality and quantity. High quality ensures that the features of the phenomena are thoroughly recorded without omitting details. Direct access to the phenomena is preferable, as relying on secondary sources, such as textbooks or others' research, risks missing key features essential to our search. Secondary sources may also be outdated or lack the precision of modern observational tools. We also want a large quantity of phenomena in our collection to reveal regularities. A pattern is a discernible regularity, and since repetition is our primary tool for identifying these regularities, a larger collection makes repetitions more apparent. For instance, a repetition that occurs 100 times is easier to detect than one that appears only 3 or 4 times. When a collection contains only 1 or 2 phenomena, repetition cannot be relied on, making regularities difficult, if not impossible, to detect, thereby rendering the universal method ineffective. A small collection is also more likely to introduce bias, potentially leading to a false theory. Ideally, the collection should be comprehensive, encompassing all related phenomena in the universe, to ensure that the resulting theory is both general and universally applicable. Once we have a collection of phenomena and recognize them as what we seek to explain, any theory we develop must cover all phenomena in the collection, no exceptions. We cannot selectively include or exclude phenomena. Our aim must be universality, ensuring all data points are connected. If our theory cannot explain a phenomenon, we must address why, acknowledge the theory's limitations, and accept that a more comprehensive theory awaits discovery. 2. Observe the phenomena for patterns by examining each phenomenon in the collection. Use instruments, measurements, and recordings to break each phenomenon down into its features, looking for regularities. The more general, consistent, and fundamental a regularity is, the better. All the tools of pattern recognition. Repetition, prediction, natural selection, and categorization apply here, with repetition of features being the most readily detected. In practice, we deconstruct each phenomenon into a list of features and repeat this process for all phenomena in our collection. We then compare these lists, looking for recurring features. These recurring features are gathered for further examination, and if they are fundamental enough, they serve as principles for a theory. Unfortunately, theory creation is complex. If only one feature appeared across all lists, creating a theory would be simple, but this is rarely the case. Instead, we often encounter a set of features, with each phenomenon displaying only a few at a time. For example, we will break down all intelligent and biological phenomena into the features of representation, recognition, reproduction, and randomization. However, if we were to pick a random biological phenomenon, we might find only one of these features prominently displayed. Such cases may indicate that our theory is not fundamental enough and that what we have found is an intermediate theory. Intermediate theories are still valuable, as they can serve as stepping stones toward a more fundamental theory. Creating a theory would also be simpler if the list of features into which we've deconstructed a phenomenon were short and complete. But this is rarely the case. Lists can be lengthy or contain only partial information. Complexity deepens when we recognize that features are patterns in themselves, each capable of being broken down further into subfeatures, which can then be broken down into sub-subfeatures and so on. The search for regularities becomes vast and intricate, resulting in a list of lists, and all we can do is hope that somewhere within these nested lists lies the regularity we are searching for. Moreover, the critical features we seek may not yet be fully described or may not even have a name. The features that make up the regularity must be detectable. The methods used to examine our collection must be able to capture and record the defining features of the underlying pattern. For example, it would be challenging to develop a theory of diseases without microscopes, to study celestial bodies without telescopes, or to understand species relationships without DNA sequencing. This principle extends beyond visual or spatial features. Temporal patterns, regularities that unfold over time, including actions, sounds, movements, behaviors, and timing, must also be considered. Therefore, tools that can record, store, and compare temporal features are essential for successfully applying the universal method. After the diligent work of collecting and observing, we may ultimately have to rely on a measure of luck to uncover the fundamental regularities needed to craft a theory. It may require deep meditation. Isolation. Endure a bout of malaria-induced fever dreams. Starve ourselves into a state of delirium. From there, with random luck, the fundamental patterns for a theory might bubble up from the depths of our mind, with the seeds of their growth planted during our initial work of observing and collecting. Alternatively, we can be strictly methodical and organized, as seen in science. We gather data, organize it into tables and graphs, making patterns visually apparent. When the universal method is applied to quantitative and experimental science, the features become variables. We search for regularities by fitting equations using the variables derived from the data we collect. If the equation fits, we explore further. In this case, repetition occurs in the equation itself, as the results of the experiment consistently align with the predictions made by the fitted equation once adjusted by the variables. 3. Use the patterns as principles for a theory. We then use the theory to make predictions, program and run simulations, and engineer solutions, thereby testing the accuracy of our theory in the process. If our theory is accurate and our principles are fundamental, the theory should not only explain all phenomena in our initial collection, but also extend beyond, allowing us to explain, predict, and engineer new phenomena. If our theory explains the initial phenomena but cannot predict or engineer new phenomena, we may have introduced bias by using an incomplete or insufficiently large collection of phenomena. In such cases, we may need to expand our collection to ensure it is comprehensive, eliminating selection bias that could lead to false regularities, and ultimately, false theories. In all cases, finding patterns is beneficial, even if we cannot construct a theory from the regularities we've identified because they are not fundamental enough. We can still use these regularities as clues in the search for a potential theory. In this context, the regularities simplify matters and serve as target outcomes that a potential theory must explain and predict. For example, the gas law's equation relating temperature, volume, and pressure was discovered experimentally before the kinetic theory of gases was developed. In practice, the universal method is implemented through representation in two primary ways. The role of representation in the universal method. 1. Features can be represented as words, symbols, or any other representative form. Since a feature is anything that can separate and group entities in a consistent manner, we can define any feature for a given phenomenon as long as the definition remains consistent. This requirement for consistency means that features are patterns and can be effectively represented as words, symbols, pictures, neurons, or any other representative forms. As long as a translation machinery exists to translate the representative form back into its original form, we can effectively store, share, and compare features using the representation instead of the actual phenomena. This gives rise to making descriptions and taking notes, literally using words to describe entities. Descriptive terms like black, blue, soft, and hairy label features. Additionally, combining words into sentences enables us to describe behavior and interactions that an entity displays, marking and storing these as features of that entity. Through feature representation, all methods of recording become possible. Representing features enables drawings of flying frogs to be made and preserved in a biologist's field journal, photos to be taken of microbes, videos to capture mating dances, and audio recordings to document the various ways organisms communicate. Representation reduces complex, temporal, or abstract features of a phenomenon to a single word or concept, simplifying the search for regularities. For example, a theory of evolution could not have emerged without pre-existing words like reproduction, inheritance, and variation in the minds of Darwin and Wallace. Similarly, a Patternist theory of intelligence could not exist without terms like representation, recognition, randomization, and pattern already defined and in use. 2. Through representation, the medium in which the universal method is carried out does not matter. Whether patterns are detected through neurons with threshold potentials, silicon transistors with machine learning algorithms, symbols on paper, graphs and tables, simulations, or language, makes no difference. As long as the medium can detect repetition and regularities, the universal method can be applied, and all the tools of pattern recognition can be used within representations to identify patterns. Furthermore, multiple layers of representation can exist to support the universal method. In human beings, the method is ultimately carried out through networks of neurons, with language, math, and science serving as intermediate layers, each contributing to the process. The ability to represent features, to capture, store, and share them across different mediums, is crucial. Representation is why libraries exist, allowing students to read books and learn. Scientific journals exist because experimental results can be recorded and shared, allowing a wider community to join in the search for theories. Representation enables a biologist to document and share discoveries from a lost jungle with colleagues on the other side of the globe. It enabled a patent clerk, by reading various experimental attempts to measure the speed of light, to develop a revolutionary theory without conducting the experiments himself. Through representation, we harness the computational power of entire populations. It is no longer necessary for the individual who collects phenomena to be the one who finds a theory to explain them. They need not be in the same room or even live in the same century. All that is required is that features are accurately recorded. The search for fundamental patterns is outsourced. 1,000,000 brains will outwork a single brain. One viable theory advances human knowledge. This is especially true in the modern age, thanks to technological innovations. We now have sensitive instruments that record finer details, video technology that captures high-definition visuals and slow-motion movements, and digital tools that free us from the limitations of ink and paper, allowing immense data storage. With the internet, we can instantly share all the information we collect with millions of others. We can use the universal method to find a theory of intelligence. The universal method is viable as long as 1. There is a sufficiently large collection of phenomena. 2. The underlying pattern's features are detectable. We have an overabundance of data. How much information, features, and their patterns has been collected and described about various biological phenomena over the past century, or just in the past decade alone? How much information has been gathered about human beings alone, our behavior and all the activities we engage in? How many high-quality recordings, experiments, and instances of rigorous documentation using modern equipment and sensors to detect finer features have been conducted by scientists and shared through academic institutions? We have an abundance of brains to find a theory. How easy is it now to go online, read articles, listen to lectures by philosophers, scientists, and biologists, or watch videos of actual neurons, bacteria, protists, and other living organisms? How easy is it to connect with others, forming communities and assisting one another in the search? The universal method is ripe for use. So, why isn't it being used? Why has it not been applied to find a complete theory of intelligence? The human-centric approach to intelligence is fundamentally wrong and is the greatest obstacle to finding a complete theory of intelligence. All that is needed to use the universal method is an abundance of phenomena to search for regularities within. But the human-centric approach prevents this. The false belief that only human beings are intelligent severely limits the reach of our search to a single phenomenon. The universal method cannot be applied. It cannot be used effectively when the collection of phenomena consists of only one. The human-centric approach is wrong. The human-centric approach has provided key insights into intelligence, but it has reached its limits. We must go beyond. What happens when we free ourselves from the chains of the human-centric view? What happens when we expand the phenomena of intelligence to include all living organisms in their activities? We will be working with big data. We will be overwhelmed with an abundance from which the principles of a complete theory of intelligence can be readily drawn. The work of every scientist, past and present, becomes a clue. How bees communicate, how ants find food, the adaptive immune system, genetics, and sexual reproduction, the active camouflage displayed by chameleons and cuttlefish, every sensory organ, all the research that took years or decades to document and catalog, once dismissed and ignored by those claiming to seek a theory of intelligence, now plays a critical role. Every nature documentary becomes a record of the intelligent phenomena. Every living organism and its activity is part of the intelligent phenomenon. The biological and intelligent phenomena are one and the same, and we go beyond. Every single human activity is now included in our definition. The printing press, the internet, martial arts, music, video games, sonar and infrared sensors, manufacturing techniques, measurement tools, blueprints, neural networks, math and science, consciousness itself. All will be included in the phenomena of intelligence. Collect a set of phenomena. Look for patterns within. Use the patterns as principles for a theory. We will use this method, the universal method, to find the principles for a complete theory of intelligence.